Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you find the content to be useful or interesting, please consider giving us a subscribe. And also any interactions you can give our videos, such as liking, commenting, or sharing, would be greatly appreciated. Let's go ahead and get into the video. What I want to take a look at is the vector multiplication known as the dot product. To motivate the idea for the dot product, let's take a look at the following. Let's look at the slope of a vector. Now we know that a vector is a directed line segment. In particular, it has a line segment, and therefore, if I was to continue drawing that, or even just looking at the line segment itself, we could imagine that it has a slope. Well, the slope of the vector is, of course, the slope of the line segment, which would be rise over the run. If I look at the vector v with coordinates AB, in other words, it terminates at the point AB, or is equivalent to the vector that terminates at AB, then the rise would be the y value, which is the y coordinate, and the run would be the a value. So in other words, it's just a ratio b over a. This would be the slope of a vector. Now, if I'm able to compute the slope of vectors, what I can then do is I could determine if two vectors were orthogonal, in other words, perpendicular. Just side note, perpendicular and orthogonal are usually interchanged when I'm talking about, say, vectors in, say, 2 dimensions or even 3 dimensions. Now, if you talk about a different type of a vector space in your linear algebra class, like if you have a vector space of functions, perpendicular doesn't really make sense, but we use the word orthogonal to generalize the concept. So in this particular video, I might interchange these. In this particular case, perpendicular is sort of more of a visual and a familiar term, but orthogonal is the more general term. Anyway, if I look at these two vectors, u and v, and I say that they are perpendicular, meaning that there's a 90-degree angle between them, how can I, or let's say it this way, what's the relationship between the slopes? Remember, perpendicular lines have negative reciprocal slopes. What that means is I can find a relationship between A, B, C, and D. I know that the slope of V, say, is B over A, and this is going to be equal to the negative reciprocal of the slope of this one, meaning -1 over D over C. Okay, so that's just basic property of perpendicular lines. They have the negative reciprocal slopes. Let's rewrite this equation, though. B over A, I'll leave that as B over A for now. The other side, -1 over C over D, I'm going to rewrite that as -C over D. Now let's cross multiply. So I would get BD is equal to -AC. Let's add the negative term over to the other side. That gives me AC plus BD is equal to 0. Therefore, if I give you these two vectors, u and v, without even looking at the graph, this equation actually gives me a test to determine whether or not they are orthogonal. Well, let's try that out with a specific example. And let's take a very simple example to start with. Let's look at the vector 2i, which would go 2 units in the x direction. So this would be, say, this is the vector v is equal to 2, 0, or if you're familiar with the unit vector notation, that of course would be the same as the vector 2i. And then if I look at the vector u, which I'm going to say u is the vector 0, 3, which of course is 3j in unit vector notation. Well, of course, visually, we see that this is on the x-axis, this is on the y-axis, so of course, they are going to be orthogonal. Now, if I use my test up above, I'm going to, of course, assign this is A, this is B, this is C, this is D. So in order to test it with this equation, I would take A times C, which would be 0 times 2, plus B times D, which is 3 times 0, and of course I get 0, and therefore it satisfies this equation, and of course this says that they are then perpendicular or orthogonal. Now if I was to take two different vectors that we can clearly see will not be orthogonal, such as, let's say I was to take the vector that goes over 2 and up 1, which puts me there. So this is V is equal to the vector over 2 up 1. In other words, it's the vector with components 2, 1. And then I take a look at the vector that goes over, let's say it goes over 1 up 2. So in other words, it would terminate, say, here. Right, this is the vector U, which goes over 1 up 2. Clearly, the angle between these is not 90 degrees. If I want to check it with this equation, just for verification purposes, I would take 1 times 2 plus 2 times 1, and of course I get 4, and clearly that's not 0, and therefore these would be not perpendicular. Again, just for some simple computations to verify that this equation does in fact work. Well, it turns out that multiplying the components in that way, of course, one application is it allows us to determine whether or not two vectors are perpendicular, but it's also going to have some other properties and some other uses as you go through your linear algebra or your Calc 3 course. So what I'm going to do is I'm actually going to say if I have these two vectors, U and V, listed here, I'm going to define this this collection right here as the dot product. So let me go ahead and formally write that up. Let me see if a dry towel will work first. It ghosts too much. Okay, let's go ahead, let's define this operation. For vectors of the form U is AB and V is CD, I guess I interchanged the letters there, but they're arbitrary, so it doesn't matter. The dot product of U and V is given by the following. The notation is to write U, and then I'll put just a dot, hence the name, U dot V, and it's equal to, well, I simply multiply corresponding components, meaning multiply the first components and then add the product of the second components, AC plus BD. One immediate consequence of this is the following. Note, U, V are orthogonal if and only if u dot v is equal to 0. Which, of course, that should be an almost obvious conclusion at this point based on the way that I introduced what the dot product was, or where it came, where one of the motivations for it is to be a test for perpendicularity. Okay. All right, let's take a look at just some straightforward computations. For example, let's define vectors u to be, let's say 1, 3, and let's say v. That's looks like that might be a little bit wet still. Okay. That's a little bit better. U is going to be the vector 1, 3, and v is going to be the vector, let's say, -6, 2. So a couple different computations with this. Part A, let's compute u dot v. Part B, let's compute u dotted with u. So u dot v and then u dot u. Solution. The vector, the product of the two vectors u and v, u dot v, given 1, 3, and then -6, 2, would be computed as follows. Positive 1 times -6 plus 3 times 2, -6 plus 6 gives me a 0. And so just, that's just the computations, just multiply corresponding components and then add the results. If I get a 0, we can then interpret that by saying that these vectors would be orthogonal. Quickly verify that. U is over 1 up 3. Over 1 up 1, 2, 3. That means that u would be the vector that terminates at the point 1, 3. The vector v will be back 6 up 2. In other words, approximately 1, 2, 3, 4, 5, 6. Approximately here. And it certainly looks reasonable that these are perpendicular. Okay. All right, part B. This says to compute the dot product of a vector with itself. So I get u dot u. Well, multiply corresponding components. So that would be the first component of u is 1, first component of the second vector, which of course is the same thing. So I get 1 times 1 plus 3 times 3 course, this is 1, this is 9, so therefore I get 10. Now, if you've talked about vectors in your class already, you've probably talked about the concept of the length of a vector. So as an aside note here, or I'll write this as a note, the length of a vector u, which is given by, say, AB, is denoted with the absolute value bars. And the way I compute that is I take the square root of a squared plus b squared. So I square each component, add it, take the square root. Keep in mind, this is nothing more than the distance formula, because if I look at a vector, say, that is, say here, say this is A, this is B, and if I say that the length, I'll just denote it by the hypotenuse. This side here would have length A, this side here, of course, has length B, and then just the Pythagorean theorem that the length, the hypotenuse, would be the square root of the sum of the squares. So that's all this is saying, is that that's the length of that vector there, interpreted as a hypotenuse. But then if I look at this computation here, notice what I have. This would be like your a squared, this would be like your b squared. So in other words, we see that u dotted with u, so the vector u dotted with u, is actually, so it's a squared plus b squared, which is actually the square of the length. So let me write that down below here, summarize that. A dot product with itself is the square of the length. As I mentioned, this is a useful tool to determine if two vectors are perpendicular, or in other words, if in an arbitrary vector space, if they are orthogonal. Well, what happens if I have vectors with 3 components, or 4 components, or 5 components? 3 components, sometimes we can get a reasonable visualization of that. Sometimes we can plot those even by hand. But once you get to 4 dimensions or higher, you literally just cannot plot them. But this still works perfectly well to determine whether or not those vectors are orthogonal. So I'm going to go ahead and generalize the dot product, and then again show you quickly how the computation works. So far, the only vectors I've used were vectors with 2 components, in other words, coming from R2. What I'm going to do is I'm going to say, let U and V be elements of an arbitrary n-dimensional vector space with real components. So vectors in R3 would be ordered triples, and R4 would be ordered quadruples, so on and so forth. So let UV be elements of Rn, then the dot product is given by the following. Same notation, of course, U dot V. What I do is, again, I multiply corresponding components, the first components, the second components, and then I add up all those products, meaning I would take the sum from K equals 1 to n of uk vk, where u1 would be the first component of u, u2 would be the second component of u, v1 the first component of v, so on and so forth. And therefore this formula gives me the general definition for the dot product for n dimensions. Okay. Now, the computation works the same way, right? If I wanted to compute the dot product of vectors in 3 space, for example, let's say u is given by 2, -1, 0, and v is given by, let's say, 3, 6, 4, then the dot product u dot v is just a natural generalization of what we did with the vectors in 2 dimensions. In other words, I'd multiply the first component, so 2 times 3, plus -1 times 6, plus 0 times 4, and then compute that. So I get 6 minus 6 plus 0 gives me 0. And just like in the 2-dimensional case, if the dot product is 0, then these vectors are, in fact, orthogonal. All right. One more example. Let's look at vectors in R4. U could be given by, let's say, -1, 2, 3, 2. And then V could be given by, let's say, 3, 2, -1, and 0. Okay. Dot product computation is analogous. U dot V, multiply the first components, -1 times 3, plus 2 times 2, plus 3 times -1, plus 2 times 0. And then compute that. I get -3 plus 4 minus 3 plus 0, which would give you -2. And again, based on our sort of test for perpendicularity, in 4 dimensions, those 2 vectors would not be orthogonal. Okay. Like I said, there's other uses other than the fact that it's just a test for orthogonality, which we can talk about in other videos. But this video here was just meant to sort of introduce you to what the dot product is and one of its important applications or important geometrical uses. So thank you for watching, and don't forget to subscribe.